This is the introduction to section 1.6. Before you press on here, I'd really like you to read the limit laws on pages 62 to 65 of the textbook. There's one key idea to take away from those, and that's what I'm going to show you how to put into practice here. So that idea is the direct substitution property. If we have a polynomial or a rational function, and a, where we're taking the limit, is in the domain of the function, then we can just substitute a into the function f of x. So for example, this first example is the limit as x approaches 4 of x squared minus 9 divided by x minus 3. So we have to ask ourselves, is 4 in the domain of that rational function? The only way it would not be in the domain of the rational function is if it causes a 0 in the denominator, and in this case that doesn't happen. So we can evaluate directly, and we get 4 squared minus 9 divided by 4 minus 3, which is 16 minus 9, or 7 divided by 1. Same function, different value of the limit here in the second example. Again, the only way negative 3 would not be in the domain of that rational function is if it causes a 0 in the denominator, which it does not. So again, we can substitute directly, and we get negative 3 squared minus 9 divided by negative 3 minus 3, which is 9 minus 9, or 0, divided by negative 6. So this limit is 0. One more example with this same rational function. We ask the same question now about 3, and because it causes the denominator to be 0, it is not in the domain of x squared minus 9 over x minus 3. So in this case, we can do a little bit of work though. We can try to do some factoring and simplification and see if we can get down to a situation where we can directly substitute. So it's really important here that we bring along the limit notation as we write this set of equalities. So x squared minus 9 factors as x minus 3 times x plus 3 divided by x minus 3. We can simplify that, and we get the limit as x approaches 3 of x plus 3. 3 is definitely in the domain of x plus 3, so we can substitute directly and get 6. Okay, I'm not making a claim here that x squared minus 9 divided by x minus 3 is the same function as x plus 3, just that as x approaches 3, their limits behave exactly the same. They're approaching 6. Okay, two more examples here. Again, same question to start. Is 4 in the domain of this function? Well, we better check by seeing what happens in the denominator. So we would get 4 squared minus 4 minus 12. That's 16 minus 16, or 0. So it is not in the domain of this function. And again, just like the previous example, our job would be to try to do some algebra to simplify. Okay, we have two options for doing algebra. The first option is we do some factoring. So we can factor both the numerator and denominator here and see what happens. Let's see, we get x times x plus 3 in the numerator. And what happens in the denominator? We get x minus 4 times x plus 3. Okay, so we can do some simplification. So this is the same as the limit as x approaches 4 of x divided by x minus 4. That simplification doesn't seem to have resulted in something where we can directly substitute. So now we need to think about what is happening here. And what's happening here? Let's think about this one step at a time. If this limit is going to exist, we would need to think about the right-hand limit and the left-hand limit. So let's see, if we think about the right-hand limit, what's happening in the numerator? Well, as x approaches 4, x is approaching 4. What's happening in the denominator? We have x is larger than 4, but getting closer to 4. So it's positive, but approaching 0. If we have a constant over something getting really, really small, that whole ratio is getting really, really large. So we get that the limit as x approaches 4 from the right of x divided by x minus 4 is positive infinity, you should also then be able to show that the limit as x approaches 4 from the left of x divided by x minus 4 is negative infinity. And what do we say when the left and right hand limits are not the same? We say that the original limit does not exist. Okay, so there some algebra didn't allow us to get rid of that 0 in the denominator, and so we need to do some further analysis to answer the question about that limit. The key idea there is that as a numerator is approaching a constant, in this case 4, the numerator was approaching the constant 4, and the denominator is approaching 0. Anytime we have a constant over something getting really small, we're approaching either positive or negative infinity. Okay, one more example. We have the limit as h approaches 0 of 2 plus h squared minus 4 over h. And now again, the h in the denominator is causing a problem because it's approaching 0. And so we'll do some algebra. See, let's multiply out. We can't factor anything in the numerator, so let's multiply it out. We get 4 plus 4h plus h squared minus 4 all divided by h. We can do some more algebra. Again, bring the limit notation along. We're asking about the behavior near 0, not exactly at 0. In that numerator, the 4's go away. We can factor out an h from both of the remaining terms. Get h times 4 plus h divided by h. And that is the limit as h approaches 0 of 4 plus h. Now we're in a spot where we can directly substitute. And that limit is 4, so that tells us that our original limit is also 4. Okay, so there's one way to do some algebra to help evaluate limits. We're trying to factor out the 0 term in the denominator. If you look at the examples in the textbook as well as the examples on the activity, you'll see the other way to do that simplification would be to multiply by 1. So we can factor or multiply our rational function by 1. So see if you can put those two ideas into practice and work on the activity for section 1.6.